Today we focus on green roof performance simulation, the concepts and frameworks that turn a living roof into decision-ready outputs. Think of this as translation. We translate a layered, vegetated roof assembly into inputs, equations, and metrics that planners and designers can compare. The goal is not perfect prediction. It is defensible decision support. What changes if substrate depth increases, if vegetation type shifts, or if irrigation is added? We will move from basic system definitions to the key processes behind heat and water exchange, then to model families, scales, and workflows. Along the way, keep one rule in mind. A model is only as credible as its assumptions, calibration, and validation evidence. In practice, the most useful simulations are the ones that change a decision and survive peer review. Here is the roadmap. We begin with what green roofs are and why simulation matters for planning and design. Next, we organize performance into domains: thermal behavior, building energy impacts, stormwater retention and runoff timing, microclimate effects, and ecological functions. Then we unpack the underlying mechanisms using energy balance and water balance. After that, we review model families from empirical to physics-based, and discuss scaling from a test roof module to building, district, and city scenarios. We close with practical workflow steps, uncertainty and validation, and a short evidence snapshot that shows how monitoring and simulation fit together. Notice that slides stay keyword-driven. The narration carries the explanation and the rationale. By the end of this topic, you should be able to define green roof layers and distinguish extensive versus intensive systems. You should be able to explain the dominant thermal and hydrologic processes, and to describe how these processes appear in models through energy and water balance. You should also be able to choose an appropriate model class and scale for a given planning question, list typical inputs and outputs, and interpret results with uncertainty in mind. Finally, you should be able to explain why validation and sensitivity analysis are not optional extras but core quality control steps. You will use these skills again in topic 3202 when we discuss tool choice and workflow design. A green roof is a roof assembly where vegetation sits above a functional buildup that protects the building and manages water. The common classification is extensive versus intensive. Extensive roofs are thin and relatively light, often with hardy low plants. Intensive roofs are deeper and heavier, supporting a wider plant palette and sometimes usable outdoor space. Most systems include waterproofing, a root barrier, drainage and retention elements, a filter layer, substrate, and vegetation. Simulation typically revolves around design variables such as substrate depth and composition, vegetation properties, drainage capacity, and irrigation strategy, all constrained by structural load and maintenance requirements. Also remember that green roofs are not maintenance-free. Simulation assumptions should include realistic upkeep conditions. Simulation matters because green roofs are multi-objective interventions with real trade-offs. A configuration that maximizes stormwater retention may increase structural load or change thermal behavior. Benefits are also climate and context dependent. The same roof can behave differently under different rainfall patterns, wind conditions, or solar exposure. Simulation supports early phase decisions when prototypes are expensive or impossible, and it provides scenario-based evidence for permitting, incentives, and stakeholder communication. In practice, the most useful outputs are comparative: baseline versus green roof, thin versus thick substrate, irrigated versus non-irrigated, and current climate versus future climate scenarios. A good simulation question is always phrased as a comparison. Compared to what, under which climate, and over what time window? Green roof performance is not one number, it is a bundle of domains. Thermal performance focuses on surface temperature and heat flux through the roof layers. Energy performance connects that heat flow to building cooling and heating demand, often through a building energy model. Hydrologic performance describes rainfall interception, storage, and release, including runoff volume reduction, peak attenuation, and delay. Microclimate performance asks how roof greening influences local heat stress and urban heat island conditions. Ecological performance focuses on habitat, biodiversity-oriented design features, and ecosystem service proxies. Simulation is valuable because it allows you to examine these domains consistently across multiple design options. Keeping the domains separate at first prevents double counting benefits when you later combine results for a business case. On the thermal side, a green roof is governed by the surface energy balance. Incoming shortwave radiation is partly reflected and partly absorbed. Long-wave radiation is exchanged with the sky and surrounding surfaces. Convection couples the roof surface to air temperature and wind. Conduction moves heat through the roof assembly into the building. Evapotranspiration converts available energy into latent heat, providing cooling when moisture is available. The key insight for simulation is that the partition between sensible heat and latent heat is dynamic, driven by soil moisture, vegetation properties, and atmospheric demand. This is why a dry green roof can behave much more like a conventional roof than a wet one. Moisture availability links the energy and water balances, which is why dry and wet periods produce very different cooling outcomes. On the hydrologic side, a green roof behaves like a miniature catchment. Vegetation intercepts rainfall and delays its entry to the substrate. Water infiltrates and is stored in pore space until field capacity is reached. Drainage layers route excess water laterally and may provide detention. Evapotranspiration removes stored water between events, restoring capacity for the next storm. Whatever remains becomes runoff, typically with reduced volume and delayed peaks compared to a bare roof. In simulation, the hard part is getting the storage release behavior realistic across different antecedent moisture conditions, because retention depends strongly on how wet the roof is before the storm arrives. For planning, it helps to run both single design storm events and continuous multi-month simulations to capture seasonality. Inputs are where models quietly succeed or fail. You need weather data that include temperature, humidity, wind, radiation, and rainfall. For hydrology, rainfall intensity and temporal resolution are critical. Geometry matters: roof area, slope, and shading. The roof assembly needs layer thicknesses and thermal resistances, plus moisture properties when hygrothermal behavior matters. Substrate parameters commonly include porosity, field capacity, hydraulic conductivity, and thermal conductivity, all of which can vary with moisture. Vegetation is often simplified but still influential via leaf area index, stomatal behavior, plant height, and rooting depth. Good practice is to document each input source and its uncertainty, rather than hiding assumptions inside the software. When a parameter is uncertain, treat it as a range and test sensitivity instead of pretending the number is known. Outputs should map directly to decisions. For thermal and energy questions, typical outputs include roof surface temperature, heat flux, indoor temperature response, and changes in cooling or heating loads relative to a baseline. For hydrology, outputs include runoff volume reduction, peak flow reduction, and time to peak delay, often linked to downstream overflow risk. Soil moisture and evapotranspiration rates help assess irrigation needs and drought resilience. Microclimate studies may output near surface air temperature, mean radiant temperature, or comfort indices. Across all domains, the most defensible output is a scenario comparison with a sensitivity range, not a single point estimate presented as if it were exact. Whenever possible, report results as differences from a baseline and include peak values as well as averages. Model families span from quick approximations to detailed physics. Empirical approaches use regressions or lookup curves derived from measured roofs. They're fast but not broadly transferable. Conceptual water balance models represent storage and release with simplified equations and are common in planning workflows. Physics-based heat and mass transfer models explicitly compute energy and moisture flows. They improve interpretability but raise data and calibration demands. Coupled building energy approaches integrate a green roof module into whole building simulation so that roof behavior affects indoor loads. At the urban scale, microclimate models and CFD resolve airflow and radiation interactions, but their input requirements and computational cost can be substantial. Model selection should match the decision, the data you have, and the level of uncertainty you can tolerate. Scale is a first-order choice. At the plot scale, you can model a test bed roof module and validate it against sensors. At the building scale, you couple the roof to indoor zones and HVAC operation, which is appropriate for energy questions. At the district scale, you often represent roof stock with archetypes and aggregate results across building types, capturing portfolio benefits. At the city scale, you combine roof inventory data with adoption scenarios in GIS and estimate system-level impacts such as runoff reduction or temperature mitigation potential. Multi-scale coupling can be powerful, but it can also amplify errors. A small parameter bias at the roof scale can become a large overstatement when multiplied across thousands of roofs. Scaling up requires careful aggregation. A validated single roof model can still mislead if city roof stock is mischaracterized. A typical simulation workflow is simple in steps and demanding in discipline. First, define the decision question and performance domain, because that determines what you must model and measure. Second, select a model type and scale that match the question and the available data. Third, parameterize with defensible inputs, ideally informed by tests, product data, or bounded literature ranges. Fourth, run baseline and intervention scenarios, plus sensitivity tests for the uncertain inputs. Fifth, validate where possible by comparing against measurements, past studies, or physical constraints such as conservation of energy and water. Finally, translate model outputs into design or policy actions, and document assumptions so others can audit your work. Write down the model version, weather file source, and parameter set so the work can be audited later. Validation and calibration are the credibility gate. For thermal performance, validation commonly uses surface temperature sensors, heat flux measurements, and local weather data. For hydrology, validation uses measured runoff hydrographs and soil moisture dynamics across multiple events. Calibration should be constrained within physically plausible bounds, and validation should use a different time period than calibration to reduce overfitting. Report error metrics and bias, and describe what was tuned and why. If you cannot validate directly, use indirect checks. Compare outputs to ranges reported in peer-reviewed studies under similar climates and designs, and show that results behave sensibly under changes in radiation, rainfall, or wind. A short, well-documented calibration beats an impressive-looking model run that nobody can reproduce. Uncertainty comes in several flavors. Parameter uncertainty covers substrate and vegetation properties, drainage behavior, and irrigation schedules. Boundary uncertainty comes from weather variability, especially rainfall intensity patterns and wind. Structural uncertainty comes from the model form itself, meaning which processes are included or simplified. Scenario uncertainty includes future climate pathways and changes in maintenance over time. Sensitivity analysis helps you rank which uncertainties matter most, so you can focus measurement effort and reduce risk. In planning, the goal is often to identify robust decisions, choices that still perform well across plausible ranges, rather than choices that only look good under one narrow set of assumptions. Even simple one-at-a-time sensitivity tests are better than none, but probabilistic ranges are stronger when time allows. Tool choice follows the question. For building energy impacts, Energy Plus includes a vegetated roof module designed for energy balance modeling within a whole building simulation. For runoff and drainage network impacts, SWMM is widely used and can represent low-impact development controls that mimic green roof behavior. Hygrothermal tools support moisture transport questions when condensation risk or material durability is critical. EPD-Net and similar models support high-resolution microclimate questions about heat stress and airflow around buildings. GIS supports roof inventory, suitability mapping, and city-scale scenario analysis. A practical rule is to avoid forcing one tool to answer every question. Instead, match the tool to the decision and the data. Tool outputs are not truth. They are conditional statements that depend on the model equations and your inputs. Turning results into design choices means translating physics into levers. Substrate depth increases storage and thermal mass, but also increases structural load. Plant selection affects shading and evapotranspiration potential, but also maintenance and drought tolerance. Drainage design shifts the balance between retention and safe overflow, which matters for both stormwater performance and waterproofing risk. Irrigation can boost cooling performance in dry periods, but changes water demand and operational complexity. Maintenance is not a footnote, it is a performance input, because clogged drains, compacted substrate, or degraded vegetation can change both runoff and thermal behavior. A good simulation report makes these dependencies explicit. A practical deliverable is a short table that maps each design lever to its expected direction of effect and the main uncertainty driver. The evidence snapshot highlights two messages. First, measurement and simulation are complementary. Studies that combine extended monitoring with numerical modeling can quantify heat transfer behavior and then check whether the model reproduces observed heat flux and temperature patterns. Second, Hydrology prediction benefits from model benchmarking. Comparative studies show that model skill can depend on calibration choices and the period used, meaning a model can look accurate until conditions shift. The practical takeaway is to treat validation and benchmarking as part of model selection, not as an afterthought. If your analysis will be used for policy, incentives, or safety-related decisions, the threshold for evidence must be higher. The goal is to learn which assumptions matter most, then focus measurement and design effort where it actually moves results. To summarize, green roofs influence multiple performance domains, and simulation is the bridge between roof design and decision-making. Inputs and assumptions drive outputs, so document them and test sensitivity. Validation is mandatory if you intend to make strong claims, and uncertainty should be communicated as ranges and scenario comparisons. Use models to compare options, identify trade-offs, and prioritize what to measure next. A model is most valuable when it changes a design choice or policy decision, not when it produces a prettier chart. If you cannot justify an assumption, either measure it, bound it, or weaken the claim. If you cannot justify an assumption, label it explicitly and avoid turning that assumption into a confident headline. This slide begins the reference list. Treat references as part of your quality control. Before you reuse a claim, confirm that the cited work actually supports it and note whether it is based on measurements, modeling, or both. Pay attention to context. Climate, roof type, and boundary conditions determine transferability. When you cite software, cite the official documentation rather than informal tutorials. In deliverables where citations are restricted to the end, keep slide text clean but make the script and reference list detailed enough that an external reviewer could audit your technical basis and reproduce your reasoning. This slide continues the references and closes the topic. A useful habit is to map each key claim to at least one reliable source and to label which claims are strongly supported versus context dependent. If a result depends on a specific climate or roof configuration, state that limitation plainly. Transparency about limits is not a weakness, it is what makes your analysis trustworthy. When in doubt, downgrade the strength of a claim, widen the uncertainty range, or reframe the result as a hypothesis to be tested. This is how you keep green roof simulation evidence-based rather than becoming a marketing story dressed up as science.